So oh, by the way, I will leave this presentation I share with you guys on this Discord, and please peer review your fellow classmates, and then you should submit by next Wednesday. I will remind you again if you didn't, but I don't want for this one I don't want to apply any late penalty. If you don't submit by then, we will not accept the submission. So please submit like before the due date like next Wednesday. So okay, now back to Kerr divergence. So Kerr divergence. So we have the definition. We look at basically it's used to kind of more or less measure the difference of like two distribution, let's say like px and qx here. So it's a two distribution regarding to some random variable x. So the Kerr divergence is a just a reminder, something like px log px over qx. So assume it's discrete, then it will be a summation. If it's like continuous, then it will be an integral. Uh, by the way, like as I mentioned, people call it divergence because it's not really a metric. This thing is not symmetric. And you see like other in other literature, like they use or textbook, they use different notation. I will stick with like just KL like this, but you see also textbook use D here, like kind of like referring to divergence, and sometimes they put DKL to emphasize its KL divergence. There's some other type of divergence, but we only emphasize on KL divergence. And one very important thing about KL divergence is that like if P and Q are the same, or like technically the same for whatever like X such that Px is non-zero, then Px is Qx. In such a case, then like KL divergence will be equal. Or like you can simply think of like if Px is equal to Qx, then it will be zero. Otherwise, it will be bigger than zero. So we show that, and as I mentioned, you can use this one application as a proof, uh, something like we prove the proof of Gaussian with maximum entropy, right? So that's we with basically with fixed variance. So we of course we need that because if variance is not constrained, then we can increase this entropy as much as we want, because we are talking about continuous random variable. So here is a maximum. This is differential entropy actually. And if you're multivariate Gaussian, then this would be like coherence matrix, right? Fixed coherence matrix. And I guess we spent a lot of time on that. And let's look at another application quickly. Uh, one is look at like, um, you can think of this as a lead to the definition of cross-entropy that is quite, I mean, when I first took like courses in information theory, I didn't even know that was cross-entropy because Wiley textbook, I mentioned that. For example, like the classic textbook by Kofer and Thomas didn't mention that. But in machine learning, this is a very kind of like um, popular terminology that you will encounter very often. So I think I should mention that. So I think of like, okay, like how, let's say like why do we have like cross entropy? How did that come up? Basically, you think of like just a simple like machine learning problem or precise classification problem. So I want to classify. Let me just give an example. Like according to my notes here, let's say I have a classification of like some individual as a different party here. So maybe it's a Democrat and a Republican and also like independent or whatever. Um, then or like others, like whatever. And then like so this is a very simple classification problem. This may be based on some kind of features like ages and or whatever like to do this kind of classification, right? And let's say now we have like two classifiers, like classifier A and classifier B, and we want to compare the performance. So let's say like for classifier A, so let's say like both classifier is a soft classifier in the sense like it gives out a soft score for that. Like for example, like it's a it's like a Republican, Democrat, and also like let's see what I think like I want to copy from my notes here. I want to make sure. Okay. Yeah. Okay. It's okay. My order is like that. Independent, uh, Republican, and Democrat. I say like that. This is a this is a classifier A, and I say this is classifier B, and also independent, Republican, and Democrat. That's like some individuals like data. Let's say go through this classifier. I have a soft score for that. So let's say like it say like with probability 0.3 or like the classifier thing that is an independent 0.3 is a Republican 0.4 is Democrat. Then let's say this is really a Democrat. Maybe I can write this to the target here. This is the ground truth here, ground truth. So the ground truth is like it's really a Democrat. So I have like 1 for Democrat and 0 for the West here. And then maybe like for classification, classify B, I have like 0, 1, 0 0.2, and 0 0.7. And then okay, maybe I should put ground truth like in just one page here. It's maybe ground truth here. This is ground truth. So erase this here. The ground truth is is 0, 0, 1 here. So if you look at that, like for this individual, like both of them like did a correct classification, right? So both of them, yes, correct. This is both of them are correct for this individual. Then maybe I have another individual, like then maybe the classifier A, it got return a score like 0.3, 0.4, 0.3, and then a classifier B return like 0.1, 0.7, 0.2 here. So then and then maybe the ground truth is a Republican, so therefore like it's a 010 like this. So again, both of them is correct, right? So this will classify as a Republican. So yes, correct. This one is correct as well. And maybe I have one more case. Let's say like uh, this one is actually independent. So the ground truth is 100, but maybe like A classified as a 0 0.1, 0 0.2, and 0 0.7. And then maybe classify B say like 0 0.3, 0 0.4, 0 0.3. So again, it looks like both of them are performing equally well. If just look at like how correct and incorrect they are. In this case, both of them are incorrect. Um, but now it's a really simple question here. Which classifier is really better? A or B? Yeah, I guess I should be pretty apparent, right? It in terms of accuracy, if you just compute the pure accuracy, at least for this given data, they are the same. But if you also look at the confidence of A and B here, like apparently like B is more certain, right? And when it's kind of like it's it make a correct correct classification, but also it's like more certain when it's correct. So and we cannot, if we just use accuracy, we cannot kind of like incorporate this information there. Um, so to kind of like compare these two classifiers, uh, one thing we can do is simply like look at like the score here, like this score, like both scores considered as probability, right? So and here the ground truth like is essentially is also like a probability distribution, even though it's like a 0 or 1, like it's like a kind of more or less deterministic. So now then we can consider all this distribution here. So we can simply use a character divergence to determine which one is better or which one is worse. Um, so then we can kind of like kind of score each of the classifier just simply using the character divergence. Let's say I call this ground truth as Q here, like the distribution as Q here. This is a PA and PB here. Then we can just look at the Q divergence between Q and PA, let's say. And then apparently like you should have like Q with PB will be bigger than equal bigger than like Q to PA in this case. So therefore like classifier B will be better. And if you look at the character divergence, what's this character divergence precisely, that will be let's say just look at this one here. This is equal to summation Q log Q over P, right? Let me skip the A there, and will be equal to Q log Q minus Q log P here, something like that, right? And by the way, this is I just rely on the ground truth distribution, right? So therefore, like this is a in comparing like two classifiers. This doesn't. I mean, it's essentially constant. This doesn't really affect the result. So therefore, we can just focus on this one, and we can define this one as like okay. Essentially, we define this one as the cross entropy. The cross entropy between Q and P. So you also see some textbook where like this or like some paper, HQ, P, but I try to avoid notation like that. It's very confusing with the just joint entropy. So if I need to write cross entropy, I probably will like cross or cross entropy Q and P, something like. And that's cross entropy basically. And any question for that? Oh wait, did I let's see if I write something. Yeah, I think I'm okay. Let's see. Yeah. And let me mention one example cross entropy. Of course, we see cross entropy used like for training classifier and so on. Like this is used very often, like when you train a neural network. Sometimes you need to specify a loss function, like very often use a cross entropy loss. So that's where we came from, this cross entropy. And one application, one, or I shouldn't say application, but maybe more or less like an example of cross entropy. It's like in text processing that I want to refer something that called term frequency inverse document frequency. Yeah, my writing is pretty bad. So the term frequency, inverse document frequency is used to kind of like to decide whether, like for example, you have a document there, you have like lots of text there, right? If you want to classify the document into like different kind of document, um, you will look at like each of the words there. Maybe you can based on the words to decide whether uh, this document belong to this or belong to that. Um, and the frequent and the importance of each of the word uh, can be estimated using this like term frequency, inverse term frequency. That's essentially just equal to the if I consider a particular document like D1 here, this is a particular document. So um, the term frequency is like how many words in D1. So like in terms of like relative like relative like frequency of like the word, this particular word in D in this document one. So it will be the number of word in D1 over like total word in D1 total words and multiplied by uh, the inverse document frequency would be like specified by something like that. We log the total number of documents over the number of document with W. So that's essentially like if look at like all the documents in the world, you want to see like how much fraction of documents will have that particular word. So and we'll take the inverse of that frequency. Even though we have a log here, just ignore the log here. So we call it like apparently this is an inverse document frequency, right? And this is a term frequency. So therefore, like call it term frequency inverse document frequency. And I will kind of explain after the break, like why we come up with this such measure there. So, okay. So let's take a break, maybe for 15 minutes again. Let's come back like around like 5:30, I guess. Like, so I'll talk to you guys then. Okay, I guess we will continue. So we kind of like ended to talk about this the TF-IDF. Like let me give I didn't give an example, but let me give a very simple example. Say I have a sentence like deep learning is very useful. Let's say it's very useful. So and if you look at this sentence, you want to kind of like classify this sentence into different contexts, say whether this is related to entertainment, like technology, and whatever. Then maybe look into each of the word there, right? And then like some word is more important, some word is less important. For example, like is most likely is not very important in understanding the context of the sentence or the document. So in this case, maybe learning is a very important word. And how do you judge like one word is more important than the other? That one way is using this TF-IDF. As I mentioned, it's a term determine like let's say if I have a long paragraph, like what's the probability of occurrence of each of the term, like say learning. In this case, like all of them is actually the same. All of them will be like 1/5, right? So because a number of word in the document for learning, there's one of them, the total number of words in the document is just 5, so it's 1/5. And then like for learning, like log, like this, I don't know, like someone has to guess, like how many documents in the world will contain a word learning, and we want the inverse of that frequency, and that probably learning shouldn't occur as many as is. Most likely is in all the document it will be more or less equal to 1. So therefore the inverse of this one is a very small. But on the other hand, like this should be like rather big. So I have a log like this inverse document frequency of like learning, let's say. Um, this should be like, I don't know, a number, at least I expect it will be bigger than the inverse document frequency of is, let's say. So and then like the overall this one probably like the I sorry, the TF-IDF of this word will be like bigger, actually probably much bigger than TF-IDF of is of learning is. So therefore, like we'll consider this one is a more important word to understand the context of the document. So how come we have this formula here, like this, the definition of the TF-IDF? So one way to understand it, like you can, from the perspective of cross entropy. So we define the cross entropy like of two, two distribution P1 and P2 will be something like just P1 and log 1 over, I have a log 1 over P2. Yeah, let me use log 1 over P2, something like that, right? So, and I can consider like this distribution, like, or I should think of like um, the word distribution inside a document as a distribution, right? So I just count how many words in the document, then I normalize with the total number of words in the document, then we form some kind of distribution. So I can, in the sense that I can compare any two documents using the cross entropies. Does it make sense? For example, like in this one, for this one will be P1 in this case, uh, will will be a distribution. Sorry, yeah. For this document, let's say this is like document one here. For this one here, will be, you think of like all the English word out there, like that's maybe like 10, I don't know, 100,000 of them. I don't know how many English words out there, and then you only have like a couple of them deep, like here. That's I have like probability 1/5, and that's a learning like 1/5, and so on and so forth. Like that would be a distribution, right? And similarly, I can have like another document have, I don't know, um, another distribution, whatever. So instead of comparing P1 with any other document, we can compare with like the average document in the world, or like think of like how word contained in like each of the document. If you think of like uh, all the document packed together and form a uh, huge document, we can say like um, consider that's a huge document, an average document, and then like um, and also we can approximate this distribution with um, the number of document with certain words uh, over the total number of documents. So we will define that as Q as the average document, the distribution average of like words in average document. So this will be defined as like the probability, like for a particular word here, will be just a number of document with this word W over like the total number of document in the world, let's say, or like in your data set or whatever, very large like uh, data set. So then in the sense you look at this TF-IDF, why we have that? It's nothing, but it's just coming from the cross entropy of any document P P1 that is a introduced. I mean like derived from a document D1 that we normalize the word frequency into a distribution as P1, and compute this cross entropy with this Q here. With Q, then I will have something like that, right? The cross entropy will be like P1 W log 1 over Q, let's say. And then you see the definition here. This 1 over Q will be precisely um, this thing here. So therefore, this is just equal to W, and P1 over W is just this number of W in D1 over total words in D1, or just simply this one here, and times log this guy here. So in the sense that this term here is nothing, but it's just the TF-IDF for word W. So then you think of, okay, if I have a compute like for the cross entropy of like any document with the FH document, it will essentially equal to the sum of like all the TF-IDF of like all the words um, out there. Then you can see that like the cross entropy is like kind of influenced by the TFI, the largest TF-IDF, right? So therefore, like it's reasonable to believe that the one with like larger TF-IDF will be more influential. So therefore, like you can have such a definition. So okay, um, that's one example for cross entropy. Besides, like just using that for as a loss function for machine learning. So next thing I like to talk about is I talk about a decision tree because it appeared in the homework. So I want to mention that earlier. So it's again like some example of like what we are kind of like using like the concept introduced in this class. So of course you probably heard of like even use decision tree before like in other contexts, like for example in some machine learning class, but we try to look at that from a different perspective. So maybe a little bit uh, in a deeper one. So so let me pull up a very kind of simple example that's introduced by an MIT professor, but he already passed away. I think it's Winston, Patrick Winston. And in his one of his classes mentioned this. I just he made up this database. I would just use exactly his database. Okay, should I no, it's okay. I probably I'll just copy it here. So it's like trying to base on like some features of some individual, and he's kind of like trying to. Of course, this is mythological. It's not for real, but he want to predict whether this is a vampire or not vampire. So let's say like he has a vampire data set here. So and the vampire data set have no the first two individuals is not a vampire, but then it's like the next three is a vampire and then not a vampire and so on. And based on like what kind of like features it has, like look at whether have someone has shadow, and then like there's some of this missing information. Like for this one, have the first one has no information, and the second one has yes, there's in shadow, and then don't know, and then no, and then don't know, and then yes, yes, and then don't know, and then like the second feature is based on like whether the individual is afraid of garlic, and then like this like say yes, yes, no, 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 no. Okay, let's see. I probably need to make sure right here. No, 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 yes, something like this. Maybe it's good to write. Yeah. Okay. Third, kind of feature is based on completion. So based on this like pale, it has like pale, and it's wadi, and wadi, and then it's average, average, pale, average, wadi, let's say. And then there's any accent, like when that someone speak, like let's say none, no, no, no. This is a heavy, and this is odd, and then heavy, heavy, and then odd, let's say. Now, the objective is that based on these features, you want to classify whether individual is a vampire or not. Of course, it is just the training data set, right? This is like what he observed from the training data set. And he want to generalize into able to classify everyone. So this is a classic classification problem. And also like we have features that is not all of them continuous as well. Actually, this in this case, all of them are discrete more or less. But of course, you can also yeah, it may not be fair. I don't know. So it's not. I don't know. I'm not kind of like he made up this example. I completely kind of like stolen from him, I guess. Uh, so and then then okay, from this class, like what do you expect? Like I can think of each of that as like some kind of the feature as like a random variable. That's like whenever we think of information theory, we think of random variables, right? So each of the individual, you randomly sampling that. So it has a chance to be a vampire, it has a chance not a vampire, and so on. Like there's a chance a shadow and no shadow, and so on. Each of them can be some random variable. Maybe I just call it S for this one, G for garlic, C, Essen, and vampire. So all of these are random variables, essentially. Now, the very simple idea, not simple idea, um, would be or the live one, like when before you're taking this class, will be something like if I want to decide like what's the best uh okay, first of all, I didn't even mention decision tree, right? The idea of decision tree is very simple. So based on each of the feature, we're going to do a split. So for example, like we based on the feature, like whether someone has a shadow or not, then I will look into, let's say, maybe a shadow. Then we determine like that's maybe like that's no, I don't know, and that's yes shadow, that's no shadow. And based on that, I will kind of like try to classify whether someone is a vampire or not, right? So if I look at this data, like more or less just from this data here, this I will use say minus sign as like it's not a vampire and plus sign as a vampire. So then like if I look at like whether it's a shadow or no shadow, you see like I have four cases here. Basically four data points here, and some of them are vampires, some of them are not. So I have like half of them are vampire, half of them are not. And then I look at my data that is actually have shadow. All of them is not vampire. And for the one that doesn't have shadow, that's actually vampire. And now I can design a very simple classifier using a decision tree. Say maybe first look at whether it's someone has shadow. If there's no, then I will classify as a vampire. Maybe this is vampire. Then if yes or unknown, maybe unknown or yes, I will do something more. Maybe I will look at the comparison. Based on the comparison, I will decide like whether it's a maybe I look at for something easier. Maybe the garlic one. That's only yes or no. Based on the garlic, maybe if like someone afraid of garlic, then I would say this is a vampire, something like that. So you can build a deeper and deeper tree or whatever, and you can trim or prune at any time. So maybe like at this point, like of course you can look at all the features and decide whether it's a vampire or not, but you can also prune maybe second level or first level and decide, okay, this is good enough. Whenever like someone has no shadow, I decide it's a vampire. Now the question is how to design such a tree, right? So and and by the way, like this is for the case with with shadow, right? So we can look at a couple more features as an example. Let's say if I also look at the garlic one. So sorry, this is a yeah. Maybe I just write G here. Garlic one has a yes and no. That like those doesn't kind of affair of garlic. This one, this one, this one, this one. Wait, no, sorry. I should say like this. Wait, I only have three data point here. Oh yeah. That's only three data point here. Yeah, all of them are not vampire. And then I have like those affair of garlic, not affair of garlic. Like some of them are vampire, some are not. Oh wait. I'm kind of confused why the setup is so weird. So a fear of garlic shouldn't be like a vampire. Wait. How do they define yes or no for this one? Garlic yes. So anyway, like, it doesn't affect the explanation here, but let's say the data set is like this. Anyway, so I thought like affair of garlic should be vampire. I don't know. So anyway, maybe this is a lot affair of garlic. I don't know. So anyway, like and I can look at like all these different features. I'm trying to build a tree, right? So now let's say like this is probably a little bit elaborate. Um, but just think of like one level at a time. Just determine which features. Like if I ask the question, like which features, like maybe I just let you guess. Like this probably it's difficult like to just get the exact solution. Like I mean within a short amount of time. Of course you can do it like honestly, but I would just let you guess. Like um if I only have one level, like if only consider one feature, which one is the best? So based on this data set, of course, it's not based on other thing else, just based on this data set. So which one, the best in the sense, of course, potentially we will have the best classification result only also based on this training data set. Of course, if I have a validation data set and test data set, the answer can be different. But like if you just look at the training data set here, now if I just want to pick one feature here, okay, someone says shadow. Actually, I don't know. I need to look at the number really. Uh, let's see if I write down the number eventually. Mm, actually, you can think of like the question mark is another label as well. For example, like um you you observe like there's either shadow, no shadow, or like I cannot determine. You can think of the last last one is another kind of category as well. Um so in terms of training, that would be just like uh, another label. So it shouldn't affect your training. But I would say like you guys like intuition are correct. But then the question like how do we determine why this is a shadow is better? Um, so I hope that like it is not kind of surprising to you. Like one very good way to determine which feature is better is simply look at the conditional entropy. So of course in this case, we only have one data set. It looks like things are deterministic. So therefore, like the conditional entropy we're computing is, you can think of this as empirical conditional entropy. So imagine now like you are going to resample this data set again. So for example, you have like these people like this all individual like A up to I don't know, A, B, C, D, E, F, G, H here, like this individual. Now you randomly put them in a room and you randomly ask one of them to comes up, and then you say like, what's the probability that not the probability, um, what's the entropy of given some feature. Now I just randomly pick that one out, and then I ask him some features. For example, ask him like the shadow feature. Like of course, right now I may be able to be observed that it's kind of weird, but maybe like uh, this I have like someone else like kind of like reported like this entire data set, and that I just asked that individual to report back to me like for this particular individual like what's his feature. Maybe then he told me that, or she told me that her shadow feature is a question mark. So based on that, based on knowing the shadow, I I can ask like what is the conditional entropy that like uh, the individual is a vampire or not. Uh, so maybe a question that just to check whether you're following me. So let's say this is like some kind of feature. Wait, how can I erase again? What I'm doing, I don't know. Yes, feature. So this feature can be like, for example, in this case, shadow and garlic and compression and acid, let's say. Now, F is good. Oh my gosh, write it here. Question. F is good, some kind of feature, if H3 given F should be big or small, A or B. I want the condition entropy to be big or small. F. Oh, okay. Yeah, the question is like, I argue that one way to select the feature is simply looking at the conditional entropy. So let's say you F is like the features, like the features and can be in this case like shadow, garlic, like compression, and so on. So for the feature to be good, I want HV given F to be big or to be small. Like either it's a case choice A will be big, like choice B will be small. Do I want V given F to be big or small? Okay, I hope it's kind of clear. Yeah, it should be small. in the extreme case, like if like this is equal to 0, then like you are done, right? Because like you are essentially V will be deterministic, right? Then actually you can perfectly classify that someone is vampire or not, given that feature, right? Um, the problem is of course, I don't know how to compare HV given F in reality, but it's like I just got an estimate based on my data for the moment. Like I can estimate this is like an empirical conditional entropy based on my current data. But um, for example, like the way just look at like HV given S, we can try to estimate HV given S, HV given S. So let's do an approximation of that. Approximate. So when I say like HV given something, like it's really meaning that okay, now if I let's say like the during testing, the sampling or like the distribution is essentially the same, identical as the training data distribution, and then we we then we can uh, as I basically think of that as like a random variable. So or like in testing, like the testing case, you can think of like it's like a random process. Also like just you pull out someone and look at that particular features, and then like based on that feature, you can also like beside the feature, you can also look at whether that one is something else vampire or not. So if this one, I say if it's equal to 0, it's essentially saying that like if I have that particular feature, then I know for sure that whether someone is vampire or not, right? That's basically V will become deterministic, right? So so therefore, like we really want this one to be small, and we can try to compute, for example, like in this case, like maybe HV given S. I try to estimate HV given S. So HV given S uh, will be equal to, that's 4 cases, right? I can look at like probability like S equal to question mark, HV given S equal to question mark plus probability S equal to Y, HV given S equal to Y plus probability S equal to N, HV given S equal to N. So based on this data alone, like let's say, what do you expect like HV given S when is question mark to be? So what is this? What do you think this one should be? Just look at this data. This is the data I have here. And basically, by the way, like plus are the vampire, minus are not vampire. My question is what is HV given S equal to question mark? So V is vampire, S is shadow, and this is a you can this one you can extract from this table here, but I already extract to you so for easy visualization. You see that when there's a when someone have a feature as a question mark, don't know, half of them are vampire, half of them are not vampire. Yes. Um. So here the assumption is like okay, of course I only have this trained data here, but assume like in reality like the distribution will be identical to my training data. So therefore like I expect like also have like half of them will be vampire and half of them are not vampire when the feature is unknown, is a question mark. So therefore in this case like V will be just a uniform distribution with equal probability of like vampire, not vampire, right? So therefore will be simply just one bit, right? This one will be just one bit. Is that uh, is that reasonable? Okay, so just to check right, whether you guys are following, then how about this one here? So how about like when um someone has shadow, what do you expect HV given S equal to shadow is yes. Yeah, it's reasonable, right? So you see like in we assume of course like this I don't know, this may be a small data set, but if we will assume that like this generalized well, that for the real data we also at least if it's not equal to zero, at least it's something like close to zero, right? So therefore like by the same token like this one is also like kind of like equal to zero here. Now how about what do you estimate like p probability s equal to question mark and like how about this? Like, what is this? Mm, this term, be careful. Like it's just probability. What's the probability? S is unknown. Mm. Yes. So here again, like we're assuming this like training data set share the same statistic as the real data set. I mean the in the real world, right? So with the entire population. So then like from our small data set here, like half of the half samples, like we cannot figure out whether there's a shadow or not. Then we'll assume that when we generalize to the entire population, there's half of the people also we cannot recognize that whether it has a shadow or not. So then like this, we will approximate just as one half, right? So therefore, like we will have like similarly, this one will be like 3/8, and this is like 1/8. So that will be like essentially just one half time HV given as like this one again, right? And with 0, it doesn't have anything, so it's just 0.5, something like that. Okay, maybe just have have an exercise for you guys. I just for the garlic case, for yeah, use use space here. For Gauss case, again, like for your convenience, let me just say visualize that like the training data here, like based on the Gauss feature, like I have if it's yes, like three of them is negative. If no, there's a three positive, like two negative. So can you try to compare H? This of course is really asking me H3 given G. It is similar to what we computed here, so it's very similar. Mm, uh, the number probably is not so nice, I guess. Yeah, that one looks right. Yeah, yeah. You look at this way. HV given G is equal to yes and no. Then your probability yes, G is yes. As HV given G equal to no, probability no, G equal no. Then if it's yes, then you see like it's kind of deterministic, right? So this part is actually equal to zero, right? Because it's like all, yeah, well, it's all negative. So then I don't even care about this, the first term here. And then the second term here, this one is like have a distribution like 60% positive, the rest are negative. So it's like something like H 0.6. So this is, by the way, I don't know, like this is I forgot if I mentioned that this is a common shorthand notation for log 0 0.6, 0 0.6 minus 0 0.4 log 0 0.4. Um, so because from the context, this is for a binary variable, with probability. Yeah, okay, I see. So, and this is what's that? So yeah, this is a 5a, right? 5a times this one. So it's more or less 0 0.61. Yeah. So, and you can try out all this like lump combination. So, and you will find that basically actually given s is smaller, so therefore like um the first like basically uh the first the first feature you can approach to should be the shadow, and you can generalize that like way. So for example, like after you have say let's say let me erase something here. So let's say like first I determine its shadow, right? And based on this data here, I can completely determine whether this is a vampire or not. So I may stop here, but here I don't know, right? So then I can ask say something like, what's the conditional probability of like V given when S is equal to question mark, and then look at like each of the other features, for example, garlic, compression, and essence, and see like which one is give you a smaller value. And then for the smallest feature, that will be like the winner. So we will stick with that features, and then we go down the tree, and then we can build the entire tree. So um, I mean, of course, it can be tedious if you sing a calculator, but if you use a computer, it shouldn't be too bad. Too bad. You should be able to write a program just to uh, kind of autonomously and yeah, make the entire process automatic. Um, so this is decision tree. I have a question like in the homework, like also like more or less using the example in the first homework, first assignment, and to also make a decision tree to decide whether the weather is a rainy or sunny. But in this case, because I have a continuous random, more or less continuous, not exactly. Uh, but we just ask a question here. Of course, you see the decision tree here. Here, I can of course ask precisely what temperature. For example, in our case, we can ask precisely what temperature um, do we have, like and then to predict what's the weather at that particular day. But we can also ask other questions. For example, in the exam, in the homework, we simply ask like, whether the temperature is larger than some threshold. So so in your decision tree, you can do many kind of like variation essentially. Um, yeah, you can do something binary, like just like checking like whether threshold or whether positive or negative. For example, even for this shadow case, I can do also binary, right? Maybe I can group this question mark and no together. So I will just say yes as one group, and no and I don't know, then will be like another group, and then like we can still form a binary tree or something. Um, so yeah, lots of like variation you can do. And maybe one final remark about decision tree is that you something very kind of like popular also like is in machine learning is a random forest. So it's like you kind of like extend this decision tree idea simply by using random tree. So what we can do is like assuming that you have many more features like, than just four here. Maybe I have like 100, 10,000 features. So we can like build a tree just using a subset of the features. So maybe just take a subset of the features and then I build the optimum tree there. Then next time I take another subset and build another optimum tree. Then we build multiple trees and then we form so-called forest. Then when we do the classification, we can just use a majority vote. So we have like maybe have like 100 trees there and see like what was the decision? Like what was the um, who what's the majority vote for that? Like which one, for example, like maybe 50, uh, 70 of them like saying it's a vampire, and 30 of them saying it's not vampire. So that will decide this is a vampire. So okay, like this is a I guess another whirlwind tour of some kind of topic like decision tree and random forest. So of course yeah, this is a really a from the perspective of a more I would say from information theory side of view. So I let's see what should be the plan next. Yes, probably should talk about data processing inequality. See from a new. So data processing inequality. Okay, say something like this. So um, if you have a Markov chain that let's say I have x and y and then let's see I probably better stick flotation in those uh, yeah okay I use xyz so I guess xyz is fine. um then we will have an inequality something like ixy will be larger than equal to ixz. um and because Markov chain is essentially symmetric, so we will also have like IYZ is bigger than equal IXZ here. So um, maybe we'll give a quick proof for that first, and then talk a little bit some implication for that. So first, if I look at the mutual information between IXY, I can use the train rule here. So remember, like IXY, if um, if I'm at IXY, if I x z given y. Mm, I'm not sure you can see that. So this will be equal to I x y and z. So the way to see that is like now the mutual information between x and y z will be like first look at the mutual information of x and y, then look at the mutual information of x and z, knowing y. So okay. So now given that I can kind of like move this term on the other side, so I have ix y is equal to ix y z minus ix z given y. And now, because I have this, okay, this is actually very simple, but like I ask you anyway, what is this? Given the Markov chain condition, was ix given y? it will be bounded by that, but it's not really. You should look at this condition as well. Like given, in general, you have IHC given y will be smaller than hz given y is bounded by hz given y, um, but they are not equal in general. Mm. Okay, okay, I guess I this yeah, I should emphasize that because this is a some of this thing you should know by heart. H is given z minus h c. No, it doesn't look like that. That one is a yeah. That one actually, if you write hx minus hx given c will give ixc, hx given z um minus h z. It doesn't in general it doesn't equal to anything, I guess. Yeah, hx z given y. Yeah, that one would be negative, I guess. In most cases, in fact, lots of cases. So I think, yeah. Um, so yeah, important to think to remember like the mutual information thing. Like and also conditional mutual information. That the physical meaning is more or less like what's the share information between two variables. Right. For example, if I have like ix and y, they this is essentially how much share information between x and y. So therefore, like when this is equal to zero, actually this is a equivalent to x and y and independent. So this is something like you should really know by heart. Like so when x and y are independent, then now so I have Markov chain like this. I guess maybe one of the problem you guys is like you kind of like forget like the Markov chain you have when you have a Markov chain like this. This is like also equivalent to saying that like x and z are conditionally independent given y. These two conditions are the same. So that does it make it more obvious like what is supposed to be? Mm. Especially looking at this one. When this is a Markov chain, well, this is kind of hard to draw. Let's see. Um, it would be something like x, y, z. Mm, yeah, that's pretty difficult to draw. Let's see. Maybe it's good for me to use different color. Let's see. Um. Uh. X. C. So y. Yeah, I left a kind of I'm not even sure like this capture like yeah actually this may not be a very good um yeah okay let me just answer my own question here. So when XMC conditionally independent given y, um, so I should have like Ix z given y is equal to 0. So this is very reasonable, right? So if you think of that, like knowing why X and C are independent, that means that like knowing why there's no shared information between X and Z. So I'm drawing this, I just trying to make sure that I see given y is equal to 0, but I am wait a sec. Actually, this is wrong. Given y is here down there. But I I mean like that may not be a very good illustration at all because that probably have other cases that have see xc given y is 0. Yeah, that's what I try to do. But here this seems to imply like let's see ixy is bigger than ixc. So when I draw that, like it imply ixy is bigger than ixc, but I'm not sure like this is always true. Um, let's see iyc, where's iyc is here. Yeah, I have doubt for that. So okay, I mean like uh for stuff like that, like when you uh I don't know whether someone tried that, but I rarely see any people try to construct a Venn diagram given this condition like that. I didn't ever see someone did try to did that. Um yeah, maybe that's something like if you're interested, you may give a try. But um for what I've written earlier, what I've drawn earlier probably is not it captured the case that like the conditional information is go to 0, but it also like need to some assumption that that is probably not right. For example, I seems to make ixy is bigger than ixc, something like that, but probably not always true and so on. So yeah, I mean don't rely on that. Like for things like I mean the Venn diagram, that one is a a quick memoir to is that word for that, like to remember some of this inequality. But um, if you try to rely on that to derive inequality, that probably will be problematic. And so, but back to what we just mentioned earlier. So this one, like, I think like you guys should remember that by heart because like this is a yeah, this is like important. And also this is like not something very difficult to remember. Like once you get a intuition of what mutual information is like really referring to. This is really referring to like what's the shared information between X and Z after knowing Y, right? And of course, like if you have conditional independence, like knowing Y, X and Z are independent, then of course like this shared information should be 0. So therefore like this should be 0, right? So this should be 0. So then I only have this one here, but then I can write I mean, expand this in the other way, right? So I can expand as I x z plus I x y given z, right? Now, because I mutual information, conditional mutual information, entropy, everything should be positive, like at least for discrete random variables. Actually, by the way, like for continuous random variable, like the nice thing about mutual information is that it's positive, even for continuous random variable. So um, yeah, but I'm not going to. Yeah, you can easily show that because it's not hard to show that because you can write mutual information as a Kerr divergence, and Kerr divergence is always positive. So unlike entropy, for example, if you write log px something like that, you do an integral like this, and then has to be positive, but log px can be negative in general. So therefore, like you can have the integral is a negative, but for mutual information, it's actually always positive. So, but anyway, like this is positive, so therefore, like I will have like this is bigger than equal to I x z. So this is a very simple proof for this data processing inequality. So why is called processing inequality? Because like one way to look at this Markov chain is like when you have, let's say, um, have x. Let me think of like something. Um, let's say uh, I want to do some classification of um, of human, like maybe just human segmentation, right, from an image, let's say. So I have like human segmentation. So I have like an image, and then I want to segment out and someone like that. And then let's say look at like I just say the input like is the entire image, like is x here, and then I process that image like I have gx here. Uh, and then I want to ask a question, like something like whether a particular pixel is a human or not. Then maybe this will be like this question will be some kind of variable c here. Now for this case, uh, there will be a Markov chain that let's see. Yeah, there will be a Markov chain like this way. So in the sense that like think of like when we will have Markov chain, it's like if I'm trying to predict something uh, for predict something like some variable here, given this variable like these variables here, uh, then the other variables will be totally unimportant. So then we will have Markov chain, right? So in this case, you see, I from the data processing inequality saying that like IXC is bigger than I CGX, let's say. Or like you can also like this IXC I may write like H. Sorry, like my handwriting is so bad. Let me move to here. So this one I can also write as a HZ minus XZ given X, right? Is bigger than equal HZ minus HZ given GX. And so I will have what, like this HX got cancelled. I will basically have HZ given GX is bigger than HZ given X. So, okay. Now you look at that. What does that mean? Like, so if I try to estimate z here, using x is better or using gx is better? Z is something you're trying to predict. For example, like I have a particular pixel here. I take a pixel. I want to see like, whether this pixel uh, is a part of someone or not. If a pixel of a human or an animal or not. Human, not human. Let's say. So it can be anything, but like I just give a kind of like um, example, kind of a little bit more concrete. Yeah, it's a binary, but you can say non-binary is fine as well. But in this particular example, it's binary, but in general, it doesn't need to be. For example, it can be a pixel. Like I can do a semantic segmentation. For example, I can have this pixel trying to recognize whether this is a pixel of a table or pixel of a computer or pixel of like anything. Now my question is simply like, so x or gx is better for predicting z. So which one is better? Yes, I think I hope it's obvious, right? Because we just talked about decision tree just now. And then we say we want to have the whatever trying to predict that thing. If we think of x as a feature, then we want HC given x to be small, right? So you see, like actually G here is just processing x. Like it can be any process, and for any process, I will have like an Markov chain like that. So an interesting implication is that like actually you can if you're not careful, like every time, of course, like in general, if this process is like invertible, for example, in the sense like if I also have like G inverse exists, like for example, like I from X I process into GX, for example, like my processing can be just doing a what I have the color image, I just change it to grayscale. Let's say like this GX is a original color image color and grayscale. Now in that case, like this G is not invertible, right? So I cannot invert this information back to X. So, but if it's invertible, then I will also have like something like that. I will have like Gx, X, and Z like this. Then in this case, like, the amount of information in Gx is the same as X. So then I will have this actually is equal. That's so. But in general, like your operation often is not invertible. As I mentioned, if I am converting a color image into a grayscale image, then the operation is not invertible, then I in general, I will have loss. That's the important part. Like sometimes it's very tempting, like to do some operation, denoising, whatever, like to your input. And then maybe your final goal is trying to do some classification or whatever. But the data processing inequality is telling you that like you have to be very careful with that, especially if your operation is not invertible. So because at least in theory, you always lost. So if you are kind of like doing things optimally, you will always get better like to use the original X than rather than using GX. So for example, like for convenience, maybe you want to change convert the image into grayscale first and then process that. But that will come with some kind of loss always. And that's you should be aware of. Of course, sometimes the loss is so small you don't care, but when you're very close to the theoretical limit, for example, like you are 90, you have accuracy 99 point something. Like if you want to push that tiny like 0.1 or like 1% accuracy, then you really need to be careful with all this loss there. So okay, that's some quick word about like data processing inequality. Uh, and I'm thinking what next I should. Uh, yeah, I don't know whether I have it. Let's see. This may take a bit longer time to talk about. Mm, oh, okay. Maybe Mikhail talked about like channel coding earlier. I don't know about homework. Like if you guys haven't worked on the homework yet, you may want to work on that because this homework is a little bit kind of like have more materials than the earlier homework, and also have like more extra credit. So you mean this one? Yeah, this is a if G is invertible. So if G is invertible, I will also have this one also. So if not invertible, I will always have it. I mean, if you here like yeah, under the square, yeah. So yeah, then you need to be careful. Like the processing is not something like you have this okay, it's not like a process thinking. It's like thinking along with the Markov chain. You know, it's not thinking along the order of your process. It's not like you have a process like okay, I first I have X, then I generate GX, and then I try to generate XC. So therefore, I have this is not a Markov chain. So the Markov chain is talking about like the how the variables are kind of interdependent with each other. Um, we okay. This is a yeah, yes. Um, any other questions? Maybe I won't start with any new material. Then maybe uh just yeah, because I have 2 minutes now. So maybe we end 2 minutes earlier this time. And uh, so do you guys have any other questions? If not, then I will have you guys okay, yeah, present have more presentations. Um 5 is we will see like if it's like I will give you guys as much time as possible. So if my experience is usually we don't use up so much time. So but if we really need to have like push the last presentation to the week afterward, that's fine. Oh, and by the way, like I guess we more or less should look at the final, uh, or like not final, but the midterm. But even though the midterm is very much near the end of the semester, we need to create a kind of like agree with a date for the midterm. Um, I'm thinking of November 10. I don't know. So after like the presentation, um, next week, then we still have one more class. I may cover some more materials, but I probably won't kind of include like lots of new materials into the midterm. Um, So you guys can ask question or like maybe we'll see. Like yeah, maybe we can do a little bit of review, but yeah, let's see about that. So how is anyone like okay with like November 10? That's what we put like tentatively on the schedule as well, like in at least for the cross Canada. So I will just like basically put up the question on Canvas, like it will be available at the class time, normal class time, 3 p.m. and then like uh, it will last maybe 2 3 hours. I don't know. Then you can upload that back like to Canvas, I guess. Uh, so yeah, it yeah, please like allocate time for that. So you may need a bit more time, like especially like for uploading. I mean, if you have something to do right afterward, like try to reschedule that, like so that like you won't be rushing like to get everything finished. So okay, so I guess I will just end here. Then I am kind of like eager to listen to you guys' presentation next week. So I'll see you guys then.
Professor, I had one question.
Yes.
You had so I had uploaded my the project, and then you had commented that though it's a good topic, it might be a little too
Oh
easy.
yeah, yes, that
So I was wondering whether I should make that as my presentation topic, and I should just use something else as my project then.
yes, actually that is good. Like I mean like the presentation is like it doesn't has to be anything you are working on. Like as long as you can explain like kind of like everyone understand and interesting. Um
Okay.
but
Yeah, because it was an interesting topic, so I thought it would be nicer.
yeah, but the
Yeah.
problem is like that's is actually quite um I should say quite I don't know how you're going to elaborate that. That's kind of difficult because
Oh
you
no, because no, I had found some papers with like so in the in the there are some research papers based on that which have like formulas like some there are 12 different formulas which
mm,
based. So I was just
yeah,
supposed.
I guess if you can elaborate in the sense like for example like in your proposal you're more or less saying like it's still going to apply on some data set and so on, right? So then
Right.
the sense would be more or less like just observing like different numbers and counting like what's the
Yes.
percentage of getting the lead in. That would be
Yes.
like yeah, to be honest it's really simple, right? Because you can get it done like an hour or something. So
Yes.
if you are going to look into really paper and get into some proof, then of course like that's fine. But like if just like saying okay have that some data set counting the number of digits and or like leading
Yes.
digits like the frequency of leading digits, that would be too simple, yeah.
Yes. Yes. Yeah. I'll look at some papers where they have tried to like derive it and done different things. So just to make it a little more.
Yeah, but that derivation, if you're just going to derive that, it may still like yeah, because it depends on like for example like you can find derivation in Wikipedia and yeah, it's a surprising result, but honestly, it's not really that um uh kind of very once you realize that okay what's the assumption, you're basically assuming that like okay it's a large range of numbers, um then it's quite reasonable to have that because you
Okay.
think of that like okay I'm yeah he's talking about Benford law, so think of that okay why one is more happen more frequently because like if you from leading one to leading two you need to go in increase like 100%, but
Yes.
if like from two to three you just need to go up like 50% so on, like from nine to one is just like 10% or 11%, so that is actually from that perspective it's quite reasonable. So if like you have a large range of number, then it's not exactly really surprising. So it's like
Right.
surprising like yeah once people like oh yeah sure then so then I don't know like how to elaborate like it need to.
Okay.
I will need to look at like further like what you going
Okay.
to do in your So,
Okay,
but
Professor. I'll anyway, I'll keep another topic just in case. If I can't find too much material on it, then I'll just present a different material. Is that okay?
yeah, sure. I'm that one for presentation is great. I mean, I think
Okay.
it's interesting. Yeah.
Okay,
But
then
for
I'll keep,
project, but for
yeah, okay.
project, it may be, I don't know how you are going to
Oh,
elaborate.
okay, okay, Professor.
Yeah.
Yeah, then I'll just
Yeah,
change
for
my project
presentation is
topic.
great. Yeah. Yeah. I think
Okay.
it's an interesting topic. Yeah.
All right, Professor. I'll do that.
Yeah.
I'll do that. All right.
Yeah.
That's all.
Okay. Yeah.
Thank you so much.
Yeah, sure. Okay. Bye now. Yeah. Let's see.